detailed design presentation. We are HAVOC Robotics, which stands for Hyper-dexterous Anthropomorphic Vision-Operated Contraption. I'd like to start off with introducing the team. My name is Crystal Boggio. This is Sean Jones, Adam Tadafayas, Jared Dellinger, and Sandy Kremen. So on today's agenda, we will be going over our purpose and goal, along with the system synopsis. We will dive into the specifications and requirements for the subsystem, starting with the motion capture. We will also talk about the project management throughout this year, and we'll summarize and conclude the project, along with what we've learned throughout this year. So the purpose of HAVOC project, or the objective of HAVOC project, is to create a system that enables a robotic hand to mimic a person's hand movement. The team's purpose is to perform research involving teleoperation of robots using motion capture equipment, along with continuing the study of overcoming dexterity limitations of specialized robotic end effectors. Also, we want to lay the foundation for future capstone projects that will allow them to further investigate teleoperation of robotics along with dexterity. So the system synopsis, there are three subsystems: the motion capture, the software, and the robotic hand. The motion capture right here, it grabs the position and orientation of the operator's hand, and it sends it to the software, which takes those data points and makes them into actuation commands. Then these commands are sent to the robotic hand, which then uses those to mimic the operator's hand movement. I will hand it to Sean Jones, who will talk about the motion capture.
Thank you, Crystal. So, motion capture overview. First, I'm going to talk you through the motion capture setup that we have set up in the robotics lab, and then I'll be talking about the kinematic equations that we use to define the angles for actuating a robotic hand. Next, I'll be going over the requirements and specifications that we tested for concerning motion capture system. So, the motion capture setup. The motion capture system that we use is provided by the school and is set up in the robotics lab. It is known as the PhaseSpace X2E, and it is set up by a series of several cameras around the perimeter of the robotics lab for maximum coverage, and it's connected to a central hub that processes the data that the cameras capture. The cameras themselves have a 13 megapixel resolution and operate at a maximum frame rate of 960 frames per second. The way that the cameras capture the data for the motion capture system is that they track LEDs that each blink at their own unique frequency that are connected to the operator's hand. It takes, and these are all referenced within a base frame that is predefined within the space that we measure. The user's hand orientation and positional data is then transferred to the inverse kinematic equations for actuating the angles. So, forward kinematics. The purpose of the forward kinematics is to define how the robot will be oriented based on the joints of each, or the angle of each joints throughout the system. For example, let's say that frame A is my wrist, frame B is my knuckle, and then frame C is the joint after that. What we want to find is the vector for going from frame A to C. And a thing to note is that the LEDs on the glove are positioned so that the location of each LED is the location of each frame. As a result, we have access to the vectors between each frame. However, to add or get the final vector going from frames A to C, we need to add the vectors going from A to B and B to C. But we can't do that as the vector going from B to C is measured within frame B, while the other two are measured within frame A. To account for this, we utilize what is known as a transformation matrix, and I'll be talking more about that in the next slide. So, the inverse kinematics. The purpose of the inverse kinematics is to calculate the joint angles defined by the forward kinematics. So, as you can see right here, for this example, frame A is now at the knuckle, and frame B is at the joint after that. On the left is the finger in its initial position, and as you can see, both frames A and B are oriented in the same way. Because of this, you would not need a transformation matrix to account for any rotations that frame B might have. However, on the finger next to it, frame B is rotated around the y-axis. Because of this, we now can no longer add a frame going from A to B and any vector coming off B and beyond. To account for this, we would use the specific matrix, or transformation matrix, ROT-Y, and we'll be calling the angle that is actuated around theta 5. Now, this particular transformation matrix is composed of 3 unit vectors of a transformation around the x, y, and z axis. An assumption that we made for our project is that the initial position of all the frames in our body are in the same position. And another one is that the vector going from frames A to B and throughout the body lie along the z-axis of the previous frame. Because of this, we can make an assumption in that the vector that we calculate using our LEDs is equivalent to the z transformation of the rotation matrix. However, to make sure that they can be equivalent, we need to first normalize that vector that we get so that it is also a unit vector. Here, you can see that in action. We're taking the vector from this LED to this LED and normalizing that vector. And then we take the rotation of that transformation, or we take the z unit vector of that transformation matrix and make them equal each other. Because of this, we get 3 equations and 1 unknown, which we can solve for theta 5. Now, this method can also be applied to a 2-degree freedom joint. The only difference is that the transformation matrix would have 2 multiplied together, but we would still have 3 equations and 2 unknowns, so it's still easily solvable. However, in the case of a 2-degree freedom joint, there is the issue of that there are 2 solutions, a lefty and righty solution where the robot can orient in 2 different ways to reach the same end effector. To solve for this, the first thing we use to solve for this is that our assumption earlier that all the frames were oriented the same way in their initial position, and the fact that we are using the atan2 function, which has a span of 4 quadrants as opposed to a normal tan's 2 quadrant. Now, for the requirements and specifications, our first requirement is that for the system, or the motion capture system, to gather positional data of the user's hand. The requirement, or the specification for this, is that we want to have the detection range within a minimum of 1 millimeter. And this is accomplished due to the fact that on the specifications of the PhaseSpace website, they state that the PhaseSpace system can, when operating at the maximum 960 frames per second, which we are operating at, it can have a detection range as small as 20 micrometers. Another thing to note is that we can also manually adjust the size of that detection range within the settings of the PhaseSpace client. So the next requirement and specifications. The requirement is that the LED shall at least have, there should be a wireless glove for the operator to use. First specification is that there need to be a minimum of 12 LEDs. This is because in our initial design, how we were tracking the angles is we were tracking the end effector of the user's fingertips. And to solve for the angles in between did not require additional LEDs. However, later on we switched to joint tracking, which required an LED at each joint to get the vectors, as I explained earlier in the mathematics. With a total, the final total of LEDs that we have are 20. For the next specification is that it'll have onboard batteries. This is accomplished due to the fact that to cause the LEDs to blink at the specific frequency, or for each unique frequency, for the motion capture system to capture, they both act as a control module and as a battery, and they are provided with the PhaseSpace system. And they are located, and we printed out a placeholder for it to be glued to the glove, as you can see right here. Next, I'll be handing it off to Adam Katafias to talk about the software implementation.
Thank you, Sean. So for our software implementation, I'll be going over our PCB schematic, our raw software implementation, and then the requirements and specifications that we tested for. Here we have our PCB printed circuit board layout. This is a shield that attaches to the top of our Arduino Mega. Here we have the pin layouts for all the Arduino Mega pins. Here we have our 18 servo connections. We have 5 force-sensitive resistor connections, a power connector, and inline capacitor, electrolytic capacitors. So here on the notation, you can see on the first pin is labeled Mega 13. This attaches to Mega 13 on the Arduino Mega R3. This is the same for the battery and ground across the schematic. We have 10 kilo ohm resistors attached to the force-sensitive resistor connections to provide a voltage divider so that we can read an accurate value across force-sensitive resistors that we may attach. For our PCB design, we've gone through 30 iterations that I'll be passing around. The first 2 are labeled version 1 and version 2, and then finally our final printed board that we had printed from Park, you can see on the screen. Here you can see the pins that connect to the Arduino Mega, the 18 servo, the 3-pin connections for the servos, the 2-pin connectors for the FSRs, and the 5 surface-mount resistors for the voltage dividers. We also have the 3 electrolytic capacitors and the power connector. We had to print this board from Park instead of in-house because the in-house boards do not have through-hole connections, which means we cannot only solder on one side. We need to be able to solder on both the top and bottom. Or you need to, if they did not have these connections, we'd have to solder on both top and bottom because we have some tracings here that have connections on both the top and bottom. I'm going to be going into the robot operating system, otherwise known as ROS. This operates as a middleware for the system that allows for processes or nodes, which is our main software code, to run independent of each other. These nodes connect to each other through items called topics, and they publish and subscribe to them to get data. An analogy for this is that a topic is like a piece of paper. The publisher can write to the piece of paper, and the subscriber can read that piece of paper and collect the data from it. Our flow chart for our ROS system starts at our motion capture system. We take in the marker position data from the system, apply a moving average filter to it to reduce noise in the system, average those positions, feed that average position to the inverse kinematics, which will give us our joint angles in radians. We then send those to an angle adjustment that will output the values in microseconds. Arduino is controlling controlling our servos based on the microsecond value, because this allows us for a greater range and accuracy over the standard servo write function in the Arduino. We then send this to the Arduino Mega and update our servos with our angles. The first node is our moving average. Our input is our task-based marker data, and our output is the average of that data. We apply a 80-point buffer. There's also a low pass filter, so we have a small delay that is caused due to that buffer. This delay is equal to half the buffer size, and since we are running at 960 hertz for our main data, it'll be 80 divided by 960 divided by 2, which is about 42 milliseconds of lag. Our code starts with initializing a multi-array that holds our data. We then check all of our marker updates for a update value. We make sure that all those values have been updated so that we do not have a singularity happen in our inverse kinematics. So we first start at the first data point, copy it into the array, and then do that until we run out of data points to collect. We update all our markers, or check that all of our markers are updated. If they are, we place it into the buffer array. If not, then we will copy our previous data set into the array. We then average across that buffer, update to our message, and then publish that message. Here you can see the result of our moving average. Here you can see a lot of noise in our raw data from our PhaseSpace system. calculating our inverse kinematics. Here's the moving average applied, and you can see a large reduction in noise. Our next node is our inverse kinematics node. This is what taking in our average task-based data and getting our joint space angles and radians. We start our ability array that holds our data again, map our points to vectors to use for calculations. And then as Sean said in inverse kinematics, we first calculate our form orientation, calculate our wrist joint angles, our finger joint angles, then finally our thumb. And we'll update our message array, and then publish the data. Our angle adjustment takes in our joint angles and radians from the inverse kinematics. Our output is going to be our joint angles in microseconds, as well as any coupling calculations that need, any coupling adjustments that need to be calculated. So first, again, we initialize a multi-array, cycle through the angles in that array. If it is, we check if our servo is reverse, because on some fingers, curling is a decrease in the servo angle, and on other fingers it is an increase. So we want to make sure we apply the right calculation for that. So if the servo is reversed, we'll add to the zero angle. If it's false, then we'll subtract from the zero angle. Then we test if the joint is coupled. If it is, we'll apply our coupling calculation. And if it's not, then we'll apply our limits to that, update our array, and then publish our data. So the requirements and specifications that we tested for, our requirement was that our system should have collected task-based data and then output the actuation commands to the robot. Our specification for this was that we should have a minimum of 6 hertz. We found this value because we found that we could operate our fingers moving up and down at about 3 times per second, and we want to sample at twice this rate, so we decided on 6 hertz. Our PhaseSpace publisher publishes at 960 hertz. Our moving average publishes at 84 hertz. Our kinematics publishes at 41. Our angle adjustment publishes at 38, and then finally our microcontroller updates the servo windows at 35 hertz. So this meets our specification. And I'll be passing off to Jared for the robotic hand.
Thank you, Adam. I will be reviewing the requirements and specifications of our robotic hand and the tests we perform to verify the specifications. Our robotic hand is broken up into 2 components that you can see here. We have the main structure that holds most of our components and electrical systems, the forearm, and they cause actuation in the joints that are housed in the hand component here. This is a CAD model. As you can see here, we have the physical printed model before you. Our first requirements were to try and mimic a hand, so we chose Sandy Cramon's hand as an average specimen between our team members. And we tried to match the dimensions of his hand to better replicate a human-like system for our then dynamic motions. Our first specification to this end is the forearm had to be a certain length, and the perimeters of the elbow and wrist had to be contained to connect to the palm and what would be an elbow. We were able to maintain our length specification, but we were not able to maintain our perimeter due to a choice to make larger servos into our system to maintain our torque and rotational angles. As for our second specification of the hand size, we had to make the hand larger in order to ensure that we could reach all the positions within our task space. Lastly, for our dimensional specifications, we decided on a grasping dimension where it could hold a 5.7 centimeter cube. We were able to verify this using a standard size Rubik's Cube puzzle. Next, we decided that the hand should have a carrying capacity similar to that of a normal human hand. We decided on 10 pounds as roughly an estimate of half of a container of water bottles. To meet this, we had to design each of the fingers to individually hold 2.5 pounds. As you can see from the diagram, the images here, we were able to meet that specification. And on the next slide, we have our wrist holding a combined 10 pounds from two 5-pound weights that were in the robotics lab. And as you can see, it is able to hold it without failure. Our next specification and requirement are about the motions of the human hand. There are 23 degrees of freedom in total on a human hand. There are 3 in the wrist area. There is 1 around this area, 1 forward and back, and then 1 left and right. As for the thumb, there are 2 in this knuckle area here, 1 forward here, and then another up here at the mid region of the thumb up here. And then the fingers have 2 in their knuckles, 1 in this midsection and 1 on the end here. However, we had to fix the fingertips so that we could reduce the number of servos we had to use so that we could fit all these servos within our forearm because it was already getting larger than our specification. We also fixed the rotation of the wrist as so because we were mounting to a Sawyer robot. As for our force sensing and error analysis, these were some requirements and specifications we were unable to meet due to our time constraints. However, we wanted to have a error analysis to show that we could accurately mimic the motions of the operator's hand, and we wanted to have a force sensing for our robot to be able to properly grasp items and not break our servos and fingers in the process. We also wanted requirements and specifications that would leave our project open to use in future capstone projects. The first being that the system can mount to the Sawyer robot. This would allow for a future capstone team to eventually use our system in a full arm motion tracking matching application. And it was met by using 4 5mm bolt holes in the back of a piece that mounts to the forearm. As for our second requirement in this end, we had that the system would not exceed a weight limit that we calculated as an average weight from an elbow down of a human male. We determined that if we were under this weight, this could also be used in a future capstone project as a possible prosthesis. As for our actuation of the system, we used 18 20-kilogram-centimeter torque servos, each with a servo horn attachment where the wires that we were using for the tendons would feed through and then be bolted in and tied to allow the tension to be held so that when the servo horn was moved by the servo actuation, it could be pulled. This was meant for all of our servos that we had in our system. And lastly, we had an idea to preserve safety. As you can see from this video, we implemented a kill switch of sorts that would stop our current flow to the system to stop all motion within the hand as a general safety in case of emergency or some sort of failure. I will now be passing.
You have to click away from the video.
Sorry. I will now be passing it off to Sandy for the final details of our presentation.
Thank you, David. So, our final demonstration, we'll get right to it. We have a video right here. So on this side, we have our motion capture system with the hand grabbing that has all the LEDs on it, so we get all our data positions. In the middle here, we have our software, which is calculating all the inverse kinematics for us, getting all those joint angles. And we're using a CAD file to sort of show that in the software. And then we have the actual hardware here. It's a little limited. We've only actually managed to get 2 fingers working because of friction problems and other mechanical problems. We'll go into a little more depth in that later. But as you can see, we can actually match the angles pretty decently. So I'm going to dive a little bit more into the project management of this entire project. So we're going to talk mostly just about budget and the Gantt chart, and then we'll go over a little bit of just to summarize the whole project. So starting with the budget, we had $600 total. We did not spend our entire budget. We saved some money, roughly $140. We did not include material costs in that, however. So we use a lot of resin and PLA and ABS to print all our parts. So we don't have that included in here. However, it's definitely cheaper than $140. In addition to that, our most expensive thing was actually buying the servos, because even though they're cheap pretty individually, we had to buy 18 of them, and so that added up to about $320. And then here's our Gantt chart. It's really not showing up very well, unfortunately. I'll explain it. But we have these darkened blocks there. They refer to the things that we've completed, and then we have some lighter blocks like here, which is stuff we're still lacking. So a couple things that we didn't manage to do is up here are FSRs. We didn't actually end up buying our FSRs because we reprioritized when we realized we had a time limit, basically. We were running out of time, and we decided, okay, we're not going to go for actual trying to get haptic feedback, so we skipped out on the FSRs. And then in addition to that, we have our tendon wiring. We weren't actually able to fully get all the tendons working all together. We did try to, we actually did wire everything, and then we tried to run some tests, but found that we were encountering huge friction problems. So actually, it's funny because the rope was fine, because the rope is an 80-pound fishing line, so it can handle the force. And the servos were fine because they take 20 kilograms/centimeters, so they're pretty strong. But our servo horns were actually breaking open as we were trying to actuate because the friction in the system was so bad. So we'll talk a little bit more about that and how we plan on fixing that in the future. And over here we have our final testing. Obviously we were able to get a couple fingers working, but we weren't able to get the entire system working. So just a summary of all our specifications and what we were able to meet and what we weren't able to meet. Of note here is our size specifications. Again, we weren't able to get things exactly the right size we wanted because we had to end up going for very large servos to make sure we had the torques we needed to move everything. And therefore, our forearm became bloated. In addition to that, we did not meet the FSR requirements because, again, time limits, so we chose not to pursue that. And this question mark here refers to our the specification that says we shall have plus or minus 5 degrees of error in each of our angles. That was something that we wrote down, but we realized afterwards we didn't really have a good method of testing that, so we can't actually really verify that yet. Now, we have ideas. We think what we might do is similar to the glove, add LEDs to our robotic hand, and then use inverse kinematics to calculate our angles, and that way we can check angles on our operator's glove versus angles on the actual robotic hand, and that way we can verify our results. So in conclusion, just to reiterate our objective here, our objective was to try and get a robot arm to imitate a person's hand. And we achieved many things. We achieved actually gathering data points from the motion capture system. We were able to take those in and convert them to joint angles. We were able to create an algorithm to convert those joint angles to servo actuation commands for our robot, and we were able to test a couple fingers at least, so we got a multi-finger system going. However, we fell short of trying to get our haptic feedback, our kind of like touch on our robot, and we also didn't have time to perfect our algorithms to make sure that we were very accurate in our angle measurements. So we have a lessons learned slide because that's kind of the point of this thing, is to actually learn something at the end of the day. So the big things we learned was, number one, our scope was too big. That's why we had to cut out some of our specifications. In addition to that, it's really difficult to actually find the correct actuators for your system. We were really struggling. Because muscles in the human hand, they're very small and they're extremely strong. You can probably hold yourself up with your, on a bar or something, with just a few fingers. And to get that to work with a robot is a challenge, a huge challenge. So we were actually thinking initially of using the linear actuators to try and get similar force, but the problem with linear actuators that are that small is that, again, they're very expensive. We were looking at servos that are small, strong, and inexpensive, and they don't exist. We did actually find a few that looked like the right thing, but upon actually purchasing them, we found out that what manufacturers don't like to tell you is the actual range that these servos can go over. We found that the small servos that we found that looked very strong could only go 90 degrees. So it wasn't enough to actually actuate our joints all the way. So that's why we ended up choosing these 270-degree servos with a bunch of torque behind them. And then finally, friction is not negligible. Obviously, friction's, we did think about friction in our system. We tried to minimize it to some extent. However, it wasn't enough. We should have modeled our system. It would have been good to model what kind of friction we had to really take account of that. And in addition, I think in the future we would probably add tubing. Now, we didn't initially add tubing because we were thinking, well, the tubing, like friction coefficient, isn't really going to change our system. But what we didn't account for was the tangling of wires inside the wrist. So we think if we used like tubing throughout the wrist, we could have actually made sure that those weren't tangled, and it would have reduced friction a lot for us. And then we also could have used other materials for our system. Instead of ABS, we could have used like durable resin that actually has a really low friction coefficient. So it could have helped our entire system. All right, and now I will hand it off to Crystal Boggio to field questions.
So I don't know if you want to follow slide numbers. On slide 24, you mentioned you had a requirement for a 5 hertz. Yeah, I think you can type 24 and hit enter.
Really? I didn't know that. Cool.
So you say you have an update rate of 6 hertz. Is that, so the reason for my question is because you said that was derived from the fact that you could move your hand up and down 3 times in a second. So is this a requirement only on the software, or are you expected to have that whole range of motion of the physical hand to keep up with the human?
That's a great question. I'll hand that off to Adam Carabias from Arizona.
So for that requirement, it was specifically for our software system, not for the mechanical aspect. Okay.
Follow on that question then. So looking at this mechanical system, what is the bandwidth of that system, which is the question I'm beginning to ask, so that I know how rapidly I should sample the output of this system and not do harm, like, for example, aliasing.
Can you rephrase that?
So you built a system.
Yeah.
Do you have an idea what the highest frequency, for example, the system can respond to? so that when I decide I want to look at the system with a computer, I'm going to sample the output of the system. How do I know how fast to sample it?
For the servo actuation, we have to test. The point, you have to test the fingers and how fast the servos can actuate those fingers. I believe that's, so we'd have to use our attach the LEDs to the robotic hand and actuate a full finger as fast as we can, and we can get our data from that and test for the sampling frequency that we need at that point.
So sample follow-up.
Yeah.
Let me ask one other question. If you could go to slide 41, please.
I tried.
Okay. 2.3.4a, it says the system shall have at most a 5-degree error for each joint. Tell me a little more about the error, whoever it is that answered that. Is that a steady state error? Is that a dynamic error?
I'll hand that off to Sandy.
Yeah, that's a steady state error. So we're looking at, once it gets to a steady state, are we within plus or minus 5 degrees of our desired limit?
Thank you. I yield.
Yes.
So, my understanding was the 4 fingers were different than the thumb, but were similar to each other. Is that correct?
Yes.
So if you got 2 of them to move, I would think if you could get 1 of them to move, you could get all 4 of them to move. So can you talk a little bit about, was it just a time constraint that, you found out how to fix it, you got 1, and then you got 2, and then time ran out, or why did you only get 2 to move?
Yeah, that's a great question for Sandy.
Yeah, again, so we actually wired up the entire system. We started by doing kind of 1 at a time. We got these 2 fingers working, and then we tried to wire the rest, and just found that through actually like tensioning everything down, and again, that big tangle of wires you have through the wrist, it just creates too much friction, so you actually stop being able to actuate these fingers that we could before. You couldn't move anything.
So if you tension all 4 of them, it just makes everything.
Yeah, it just makes too much friction.
And if you could go to slide 24. Sorry. You mentioned coupling in some of the joints. I'm not sure you explained exactly what that was, or I missed it. Could you
Yeah.
clarify what you mean by that?
Yeah, so the coupling of our system, initially when we first tied our tendons, we had a 1-to-1 on each joint for the servo angles. But once we tensioned these tendons, when we moved the proximal phalanx 90 degrees, the middle phalanx would actually stay upright. So we had to account for that change in the proximal phalanx of 90 degrees and apply that to our middle phalanx. So that was the coupling.
Okay. Thank you.
What was your intention of the haptic sensors? Were you just going to detect the force applied, or were you going to try to provide feedback to the articulated hand?
That's a great question for Sandy.
Yeah, so the idea of that was to be able to detect when we were actually grasping something, because we were thinking, well, if you don't know that, then you could drive your fingers together even if there's something in the way. So the idea was to actually prevent the system from breaking itself. And if we went a little bit further, yes, we could maybe implement some sort of haptic feedback control, but again, that's expanding our scope, which was already big enough anyway.
Question for Sean. You mentioned you had 3 equations and usually 1 or 2 unknowns. Did you ever find that those equations didn't match up and give the same solution? And if so, did you have any way of resolving that?
I personally didn't encounter any situation where the equations resulted in a different solution. As I mentioned before, we took that into account with our initial setup and the fact that we were using ATAN2. And once we used those 2 in conjunction with each other, that resolved any issues of unreliable data.
You also mentioned that you wanted within 20 millimeters accuracy, right?
It was with the requirements were within 1 millimeter accuracy, and the maximum that the PhaseSpace can achieve is 20 micrometers.
Oh, micrometer. So that's smaller than if you put the glove on Sandy, that's probably more accurate than the LEDs are resting on his knuckles, right? Because those are probably gonna shift around a little bit.
Yes.
Okay, so I guess my question is, for generalization purposes, you know, you've got the glove and there's obviously some slop in there, and you've got specific to Sandy, looking to the future, other hands and so forth, and making sure that your LEDs are lined up. Do you have any ideas as to how to make that a better fit and something that would work for multiple hands and still map over to this hand?
Yes.
That's a good question for Sandy.
Yeah, I just want to answer that. So the thing about the glove is that, yeah, you're right, it does like expand and contract a little bit depending on who's wearing it. Because the way we calculate our angles is the vectors like between these positions. It doesn't actually matter like how long they are or how short they are. We're just trying to get the angles between them. So theoretically, anyone could wear the glove and still get the same angles.
Ask another pretty high level question. The prior question about haptic sensors on the end. As I was watching the video, there's a fair bit of latency between the person moving their hand. The video seems pretty quick with my eye, which is only about 20 hertz. But the mechanical system had a fair bit of latency. So top level question and then a follow on. Would you consider that overall system an open loop system or a closed loop system?
I don't think you can, no, I guess it's an open loop system. Because,
Thank you.
you can
It's early, go on.
Yeah, I was just thinking that you can in fact speed up your system by using feedback, so essentially.
Therein lies the rub.
But we didn't implement like a direct control or anything because there's already PD control inside the servos.
So there's some sort of controller wrapped inside the servos, but if you wanted to be able to control dynamically the motion of the
Yes.
fingers, you may want to go to closed loop.
Yes.
And at that point, the latency might cause some small problems.
Yeah, but we would also have to model the PD controllers on the servos, which I think would be probably a monumental task in itself. So.
You guys, where I'm going is you talked a lot about handing these off to the next group. So I'm starting to, have you laid any of that foundation to hand off to the next group, what the challenge is? That seems like a logical progression. Any thought given to that?
I think that in most of our idea when we say handing off to the next group is at this point our hand mechanically it sort of works, but I think they could definitely improve it. So I imagine right now like handing off to the next group means they make a better, more efficient, maybe under actuated hand, so it needs less servos, something like that. What we've established is the system where you can actually get your data from motion capture, convert that to angles. So that's really what we're trying to establish and pass on and document.
What was your basis of your 80 frame moving average for your noise reduction? Did you do analysis? Or did you just say, well, 960 hertz and 80 hertz kind of place in versus a filter or some other methodology of noise reduction?
That's a great question for Adam.
Yeah, so we did our analysis in the prelim semester with MATLAB simulations, and we sampled the 960 hertz PhaseSpace wood in our simulation, and we chose a buffer of our 80 frames from data that we found to get a small enough lag on the system so that we don't have a large delay between the angle updates and a wide enough so that the noise would be reduced a fair amount.
Did you look to make sure that you weren't going to cause any aliasing in the system or anything of that nature?
I don't believe we had on that.
One thing I think I noticed in the plot of the data, you took out the person's heartbeat.
Any other questions?
If we have time, do we though?
I think so.
Comment first, if you will. Congratulations, this is some very good work. I'm impressed that undergraduates have been able to pull this off. And maybe I'll ask you to give some advice to yourselves. So if you were to be able to where you are now, go back and give yourselves advice at the beginning of this project, what would it be?
I think it would be to really trim down what our focus was. We had a bunch of really cool ideas and we wanted to do them all. And I think halfway, 3/4 of the way through the year, we realized, okay, we've got 5 different ideas and we need to choose one. What's our goal? And so if we were to go back, I believe, the motion capture we all agreed on, and I think we should have just really focused on that and trying to improve and really, make sure that we get all 4 fingers, all 5 fingers working, and I think that would have been a possibility.
Anyone else?
Do you want us all to?
No, it's up to you.
Yeah.
I can go on.
Anybody else
I
want to
think,
hear yourselves?
I think there was a suggestion early at the beginning of the year, which instead of doing a robot hand for this project, to just use the Sawyer robot, which has 7 degrees of freedom, set of control, and use motion capture on like your arm to imitate arm motion. So I think that would have been kind of would limit the scope a little bit, so that would have been a bit better. Also, the Sawyer robot can be controlled through ROS, so we would be letting everything through that. That's an absolute possibility. I also think that if we were, going to stick to the robotic hand, it would have been a good idea to push for actually under-actuating the joints or using less servos somehow, or instead of using servos, use less actuators. I actually saw there's research that's been done where they take rotors and like 2 strings and they'll spin the motor, and because the strings wrap around each other, you create a bunch of tension. You can actually actuate things that way. That would have been a really interesting project as well. So I think mainly it's just don't go directly to servos. Really rethink how you want to actuate the system.
That change I probably would have told myself earlier in the prelim semester is that, as I mentioned earlier, we switched from following the end effectors of the operator's hand to following the direct joints. And the reason for that is because we found partway through is that the math behind trying to follow strictly the end effectors is much more complex and much more unreliable than just following the joint angles and using the robotic kinematic equations that I presented to you earlier. And this would have saved quite a bit of time in just trying to, the long nights of trying to hash out what equations could I do to possibly find the angles between a knuckle and like a fingertip and actually make it look realistic.
Yeah, I have to say for mine to simulate everything, we stopped short of the joint angles. Instead of modeling all the tendons and the friction in the system and all that, if we had accounted for that and simulated, we would have been able to find a lot of our problems earlier in our design process.
For me, I would have given my past self a better estimate on the servos that we would need for the system, since I had to redesign the forearm multiple times as we changed which servos we were using, and that caused several delays. I would have also told myself to get more of a team collaboration onto the software, because if we had gotten that done,